Now that we have a little introduction to matrices out of the way, let's talk about how to actually represent a system of linear equations using a matrix. And to do that, let's go ahead and bring back both of the linear systems that we looked at in the previous videos when we talked about solving a linear system with 2 unknowns and solving a linear system with 3 unknowns. Now, we hinted at it in the last video, but really when we're setting up a linear system or when we're representing a linear system with a matrix, all we really need to focus on is staying organized. And here's what I mean. Let's look at the system here of 2 linear equations. So we've got 6x plus 3y equals 27 and negative 5x plus 2y equals 0. The thing that we want to focus on is keeping all the values from the first equation in one row of the matrix and all the values from the second equation in another row of the matrix. And then in addition to that, we also want to make sure that all of the values associated here with the x variable are lined up in one column, and all the variables associated with the y value are lined up in another column, and furthermore, that all of the constants over here on the right-hand side are lined up in another column. So we're just staying very organized about the way that we translate values from this linear system into a matrix. So if we just wanted to represent the coefficients from the left-hand side of this system in a matrix, here's how we would do it. We would have a 2 by 2 matrix. We would take the coefficients from the first equation, 6 and 3, and we would line those up in the first row. So 6 and 3. And then we would take the coefficients from the second equation, negative 5 and 2, and we would line those up in the second row. And like I said before, all we have to do is be careful that the coefficient on x, negative 5, gets lined up under the coefficient on x from the first equation, 6. So the negative 5 needs to go here, and the 2 needs to go here. Because now, if we go ahead and call this equation 1, and we call this equation 2, what we've really shown in this matrix is that we have here the first equation and the second equation across the first row and second row, and then we have x and y down the first column and second column. And then we could close off the matrix, and this is a matrix now that represents the coefficients from this linear system. We can call this the coefficient matrix. So when you hear coefficient matrix, it means it's the matrix of coefficients on these unknowns from our linear system. But this matrix doesn't give us the full picture of the entire linear system. We don't have actual equations unless we include these values 27 and 0. Because if we only have this matrix and we pull these back out, all we have here is 6x plus 3y and negative 5x plus 2y, and we can't solve this for values of x and y. These are just expressions. We don't actually have equations here. So in order to actually use a matrix to represent the entire system, what we do is we augment the matrix with the constants from the right-hand side. So we augment the coefficient matrix to include the constants from the right. So 27 and 0. Here's what an augmented matrix usually looks like. Sometimes we just put in 6, 3, 27, and then negative 5, 2, and 0. Sometimes it just looks like that without necessarily this gap. But usually what we do is we draw a line in between the coefficients and the constants. And so that clearly indicates to us what's what in the matrix. And again, we kept everything organized. This was everything from equation 1 in the first row, equation 2 went into the second row, and then here we had the variables x in the first column, y in the second column, and then our constants, so we'll say like capital C to indicate the constants from the right side. So this is now an augmented matrix that represents this linear system, and later on we'll look at how to use this matrix to solve the system or to come up with the solution to the system. Now if we want to represent this linear system, 3 equations in 3 unknowns using a matrix, we do the exact same thing. We just make sure that everything from equation 1 goes across the first row, equation 2 goes across the second row, equation 3 goes across the third row, and then we line up all the coefficients on x in one column, y in a second column, z in a third column, and then the constants get augmented on in a fourth column. So if we sketch out a matrix here's what it would look like. Let's go down the columns this time and take the coefficients on x. So we have 3, -1, and +1. So 3, -1, and +1. On y, we have -2, -5, and +4. So -2, -5, and +4. Notice how I'm always including the sign of the coefficients and the constants, whether it's negative or positive. On z, we have +1, 4, and -6. So 1, 4, and -6. And then we'll augment that with the constants 2, 1, and -9. So 2, 1, and -9, and then close off our augmented matrix. And this matrix now represents this linear system. Now, these examples were both already teed up for us, but there's one thing we want to be really careful about, because sometimes you won't be given a linear system with a perfect setup like this. So for instance, this system, we had an x, a y, and a z term in every single equation, and they were always written in order. It was always x first, then y, then z in each of the 3 equations. But sometimes some of the equations will be missing variables, and sometimes they'll be out of order. So let's just mix this up a little bit. Let's say that this first equation, we're going to make up an equation. I don't even know if it has a solution or not. We're just going to mix up something different. So let's change this first equation. Let's maybe say it was given to us as 2y, and then maybe the z term isn't there, and then we have equals 2 minus 3x. And then this second equation was written as is, -x minus 5y plus 4z is equal to 1. And then the third equation is maybe a 9 plus 6z is equal to y. So I just made up a totally random system, but you can see how it's mixed up. So before we translate this into a matrix, we need to make sure that we're accounting for everything, we're not missing anything. Again, the key here is staying organized. So the first thing you want to do in a situation like this is you want to make sure you know how many variables you have and what they are. So if we look at this first equation, we've got y and x, so we have x and y. The second equation we see is z, so now we know we have x, y, and z. The third equation, we have a z and a y. We've already got those in our list. So we know we have x, y, and z. Now we want to go ahead and reorder each equation. So we have x, then y, then z, and then the constant on the right side. So for this first equation, if we add 3x to both sides, we'll get 3x plus 2y. And then we would have this equal 2. But remember, we need x, y, and z. So in order to put in a placeholder here for z, we want to go ahead and say plus 0z. That doesn't change the equation at all. Adding 0 to something won't affect the value of the equation, but it's a placeholder so that we don't forget to put a value for z into our matrix representation. So we'll rewrite this as 3x plus 2y plus 0z is equal to 2. For the second equation, we have x, y, and z already in order and the constant on the right side, so we'll leave that as is. -x minus 5y plus 4z is equal to 1. And then the third equation, we don't have an x, so we'll go ahead and put in a placeholder 0x. We want to then have y, so we'll subtract y from both sides. That'll give us a -y over here on the left, so minus y. The 6z is already on the left, so we can say plus 6z. And then we'll subtract 9 from both sides to move that 9 to the right, and we'll end up with a -9 on the right side, so equals -9. Now that we have everything in order, it'll be a lot easier for us to represent this as a linear system. I would always recommend when you're given your linear system mixed up like this to rewrite it before you transfer it into a matrix so that you don't mix up a sign or forget some particular value. So now we can translate the coefficients on x, 3, -1, 0. So 3, -1, and 0. The coefficients on y are 2, -5, and -1. So 2, -5, and -1. And the coefficients on z are 0, 4, and 6. So 0, 4, and 6. And then we'll go ahead and augment that with 2, 1, and -9. So 2, 1, and -9. And then close off our augmented matrix. And this then is the representation of this linear system in matrix form.